In the last class, we have studied bus structure, and bus is the most important component which connects CPU with memory and peripherals. Today, we shall study more specific bus structures, both parallel as well as serial buses. To recapitulate what we did in the last class, we studied single board computers as examples of embedded systems. Single board computers are nothing but a PC put onto a single PCB. So, that single PCB satisfies all the basic characteristics of a PC architecture. The bus which runs on that board is typically ISA bus or PCI bus that we had studied earlier, and you have serial and parallel ports. So, in fact, SBCs provide all the flexibility and power of a PC with very small space requirements. So, basically what has been done is that footprint of that card which is being used has been reduced so that it can be used in an appliance. The basic motivation of doing this is that your software can be very easily ported and you do not spend time as well as money in using tools targeted for specific microcontrollers like PIC and ARM. In fact, PC104 and PC104 Plus meet the need of SBCs. In fact, these are nothing but re-specification of ISA and PCI bus suited for small footprint devices. In fact, the basic bus architecture is that of PCI bus. In fact, we looked at this diagram in the last class also. We are just looking at again in order to understand its dynamics. So, the most important thing to note is that this is an hierarchical bus structure. In fact, there are three levels of hierarchy. You have got the CPU bus, you have got PCI bus, which is the bus which connects the CPU with other peripherals, and there is an ISA bus which is for the slower devices. In fact, among the three buses in this hierarchy, CPU bus is the fastest bus, and you will find that we have got bridge, a PCI host bridge, which actually does the communication between the CPU bus and other peripherals whenever it is required. The most important and interesting thing to note, the communication with the DRAM. We have already studied that DRAM is a slower device, and the CPU bus will be pretty fast because CPU is working at a higher clock rate. So, the PCI host bridge provides the communication interface between the fast CPU bus and that of the slow DRAM device. In fact, it also provides connectivity to the basic IO system ROM as well. Further, this PCI host provides connection with PCI bus. The motivation is the same. Here you have got slower devices. So, the slower device access will be on this PCI bus, and this bridge will actually control the communication between these two buses. In fact, this basic architectural model you will find today in most of these buses which are targeted for connecting high speed processors with peripherals and memory. What is really a bridge? A bridge is a slave on the first bus and master of the slow bus, because bridge is actually sitting on both the buses. And if I look at a typical master slave configuration, then your CPU will be the master for the faster bus and bridge will be slave over there. So, the bridge will take commands from the first bus which has got the CPU, and it will become master in the slower bus for carrying out the transactions, read and write transactions with the slower devices. So it will issue command on the slow bus. So effectively it can become a master on the slow bus. So its basic responsibility is returning results from slow bus to first bus, as well as if something has to be put from first bus to the slow bus. It also functions as what is called a protocol translator, because I can have the two buses working with different transaction protocols. So a request from one bus has to be translated into a request compatible with the protocol of the slower bus. So that translation is also carried out by the bridge. So in fact, bridge you can consider is actually an additional hardware. In fact, in very simple case, a bridge would be simply implementing a protocol machine, that is a finite state machine, but in more complex cases like PCI bridge, it will be as good as that of a controller with its own registers and control logic. In fact, if I now look at system on chip, what is a system on chip? It's actually what we have seen in terms of discrete components on a PCB that being put onto a silicon element. And a system on a chip can have multiple processors as well. In fact, we have already seen OMAP, which has got a ARM as well as a C55 DSP. So this is an example of a system on a chip. So there will be a fast bus, okay. So you have a system bus, you have a bridge connecting it to a slower bus to which this kind of input and output devices can be connected, okay. There may be also custom interfaces. Here an example has been given for an MPEG encoder. So if I have the data, that MPEG encoder converts it, okay, and it uses a kind of a custom interface to write that data through the memory controller. It may also invoke the DMA controller, and DMA controller is actually sitting on this bus transferring the data from this special purpose peripheral to the corresponding devices. It may be even to the memory. So what we say, that system on chip requires busing systems to connect various components, including one or more microprocessors, memory, peripherals and special logic like your MPEG encoder. Now here obviously my bus specification and bus protocols have to be different from what we have considered and seen for a PCB requirement. So in this context we shall look at ARM processor bus interface. In fact, many of the SoCs use ARM CPU core as a main driving CPU. So ARM provides advanced microcontroller bus architecture, and this bus is called AMBA bus. ARM processor uses AMBA to interface to the system bus, okay, that CPU interfaces to the system bus. And what are the advantages of this kind of interface definition? It standardizes bus interface. It allows increased reuse of IP in designs, because I can pick up another IP which is compatible to the AMBA interface, and I can put them together to design my own SoC. And it enables the creation of upgrades and various families of devices, because these devices need to be just compatible with the bus. In fact, this is the basic underlying theme for definition of all the buses and the necessity for defining a kind of a fixed protocol for the buses. So once I have devices conforming to the bus protocol, they can be used in a system without the necessity for developing special interfaces. In fact, this is the key motivation for defining buses and also studying the bus structures. So you go back to the picture that we had already seen earlier. So you have got this ARM processor, it has got its bus interface, making the interface compatible with what is called AMBA bus. Now obviously when I am having a bus and definition of the signals, they may not be always same as that of the signals being provided by the core, processor core. So I need to have an interface unit. So this is the internal bus. This bus connects its what we have called the system bus. This bus connects a processor to the on-chip RAM, as well as this provides an interface to the external bus interface. So these are external devices. Since it's a multi-master bus, actually there would be an arbiter. We had discussed what is the role of arbiter. Arbiter arbitrates between the requests coming from multiple masters sitting on the bus. And just like PCI bus, here also I have got a bridge. The function of the bridge is the same. It is connecting the high speed system bus with the low speed peripheral bus. You have got a timer, interrupt controllers and other devices which should be lying on the peripheral bus. And what is important, this AMBA is basically on-chip bus specification. Your PCI 104 or 104 plus were not really on-chip bus specification, but actually external to the chip PCB based bus specification. So it is again, as we have seen, it's a multi-level bus. It has got at the system level, the bus is called ASB or AHP. These are two different bus specifications and they have got different capabilities. They define the structure of the system bus. We shall not really distinguish between them. We shall look at their characteristics more in reference to AHP, and these parts will translate in most of the cases to ASB as well. So here the objective of this bus to connect high performance modules. Then APB is advanced peripheral bus, simpler interface for low performance peripherals. In fact, the whole bus supports what is called 32-bit, 64-bit as well as 128-bit data bus transfers. Okay, fine. Using a 32-bit address bus, and this is the basic characteristic of ARM. It can also be used for doing smaller byte transfers like that of smaller word transfer, half word, byte, etc. It is a synchronous bus, non-multiplex buses that support busting, that is bust mode transfer, as well as that of pipelining. So system bus interconnects a processor in an SoC with memory controllers, on-chip memory and typically DMA controllers. Slower peripherals are connected to the slower and simpler APB peripheral bus. And this system and peripheral bus obviously is expected to run at different clock rates. And they link via a bridge that buffers data and operations between the two buses. Why it needs to buffer data? Because there is a mismatch in the speed between the two buses. These AHP and ASB, which are really the system buses, are typically multi-master buses, and they use a central arbiter. That is, the basic arbitration scheme is based upon a central arbiter block. And each transfer on this bus has got an address as well as a control cycle. These buses, I already told you, is pipelined bus. What does that mean? They can start the next transfers arbitration and address phase while finishing the current transfer. While the current data transfer is taking place, it can start the arbitration for the next phase. So obviously, since these are pipeline, the speed at which the transfer takes place is much more. So how it works? AHP puts an address on the bus followed by the data. If it is a write, so the master provides the data. It supports wait state insertion and uses a data valid signal which is called H-ready, which is just like a ready or a wait signal that you find with ARM. It has a separate read data and write data buses. Okay. It supports bursts. Okay. So, bursts can be in terms of 4, 8 and even 16 watt transfers at one go. And these bursts can be address wrapped. That is, this burst would staying within a fixed address range, and slaves can insert wait state to adjust its response. In fact, if you remember, we said that if it's a sequential access, the whole issue that comes up is you can generate address once, you can arbitrate and generate address 1, and the master can have the bus for transferring up to 16 words at one go. It can be even undefined length bursts, as well as there can be simply single transfers. So, all bus operations are initiated by bus masters, which can also be slaves. So, there is a interchangeable role between master and slave. The master generated address is decoded by a central address decoder that provides a select signal to the addressed bus slave unit. The bus master can lock the bus, reserving it with the central arbiter for a series of locked transfers. Okay. So, this can enable it to take over and initiate fast transfer on the bus. So, how does really the arbitration takes place? Each master on the bus has got a unique identifier. Okay. So, it is a multi-master bus. So, each master has got a unique identifier. So, master X requests for the AHP by issuing what is called a request signal. X is the indicating the corresponding master's name. When bus is available, the arbiter issues what is called a age grant X to master X. So, master knows that bus is available with him. Okay. Upon receiving the grant signal, the master issues address and control information to indicate the type of transfer. So, the master has to first get the bus and then do the transfer. So, while one transfer is taking place, another master can initiate a request for the bus which arbiter can process. Okay. So, the whole thing can be actually overlapped in time. So, if you look into it, the basic picture is something like this. So, I have got this as an central arbiter. These are multiple masters which are actually sitting on the bus. They will generate the request and arbiter will generate the grant once it resolves the priority. If there are multiple requests coming in at the same point in time, arbiter will use its own priority scheme. We had discussed a priority scheme in the last class. Will use its own priority scheme to identify which master now gets the bus. Okay. Once it knows, it enables these buffers. Okay. Once it enables these buffers, the address would flow from the corresponding master to the target slave device. First, the address would go. In fact, the whole point is once you have the address, the decoder actually knows which of these is to be enabled and accordingly which slave device is now targeted to receive the data. So, each slave device is provided with an address, and using that address, master refers to the slave device. In fact, the slave unit has some options as well. So, slave unit has the option to terminate a transaction as an error. If it finds that there is an error condition currently valid with that peripheral, it can flag an error. it can signal the master to retry or split the transaction for later completion. In fact, split transaction is an advanced feature which is available with AHB. Now, split transactions enable the slave to defer the operation until it is able to accomplish it, and thereby releasing the bus for other accesses. Okay. So, what does split transaction really mean? In fact, the slave, once it has received a request for a transaction and it finds that it is not able to complete the transaction, it will indicate to the master that the transaction can be splitted. So, the slave signals a split transaction and saves the master number, because each master has got a unique ID. I told you that earlier. When it is ready to complete the transaction, the slave signals the arbiter with the master number. Okay. When the arbiter grants bus access to the master, it restarts the transaction. In fact, the convention is no master can have more than one pending split transaction. I hope you have understood why this transaction is called a split transaction, because master had initiated a transaction. For some reason, slave is currently not able to complete the transaction. Okay? So, it signals a split transaction and retains the master number. Then the slave requests the arbiter that I am now ready, so please provide the bus to the master to carry out the transactions. As long as it is not ready, the bus becomes available for other operation. Okay. So, this is a more sophisticated way of doing a transaction with a peripheral. So, what are the AHB signals? If I look at these as an AHB master, this is a kind of a conceptual model. There can be any CPU or a DSP can be an AHB master. The whole issue is that the interface, bus interface unit of the AHB master should have compatibility with these kind of signals. Already we have seen that it will generate the request. This is a request to the arbiter. It will get the grant from the arbiter. If the slave wants to introduce wait state, this is the input which will come from the through the wait state. The response gives the status, okay, the response from the slave, and these are obviously address and the control signals. These are address and control signal. This is the data, okay. This is you have got your write data bus as well as read data bus, which are two distinct buses, okay, and these indicates the transfer type. You have seen that there were signals called HPROT. In fact, this is point we have not discussed earlier. These are called protection control signals, provide additional information about a bus access. It is primarily intended for use by a bus decoder when acting as a basic protection unit. Okay. So, the signals indicate if the transfer is an opcode fetch or data access, if the transfer is a supervisor mode access or user mode access. Okay. The signals are driven by the active bus master and have the same timing as that of the address bus. Okay. So, these are protection information and we call these as a protection data. These signals really do not provide the protection, but these signals actually encode what? The status of the current transaction. By making use of these bits, the bus decoder can function as a basic protection unit. A simple example is, if a transaction is taking place in user mode, it will not be permitted maybe to access register of another processor or maybe another memory area which is granted simply supervisory access right. Okay. So, that protection can be ensured in hardware through the bus decoder, and that is why the protection signals form part of your bus signal specification. Okay. Some more AHP signals are size. In fact, this size we have already seen in the context of ARM signals, memory interface signals also, and it is consistent in that context. And H-trans, these transfer signals indicate the type of next transaction, which may be address only, non-sequential or sequential. These signals are driven by a bus master when appropriate grant test signal is asserted. Okay, so that to prepare the devices to expect what kind of transactions would take place next. Let us look at its timing diagram. In fact, I said that they are synchronous bus. Okay. So, if it is a synchronous bus, the whole thing is actually driven with respect to a clock. So, all transactions I said has got a address and control phase. This is followed by a data phase. In fact, the address is provided on your H address line, and you have got the control information coming in. So, this control information is also provided in the address phase to prepare the devices for the targeted transaction. Okay. And this, if it is a write operation being initiated by the master, the data should be available at this point itself. Okay. And if and when there is this H ready signal, okay, what happens? If you have this, when you have this H ready signal, depending on the status of the H ready signal, there will be wait states introduced. Okay, so in this case, your data which is here it's delayed. Okay, I introduce wait state over here. Similarly, for the read also there will be the data phase which will get delayed. Now, this timing diagram is very similar to what we have seen in the context of a simple memory interfacing. But the overall transaction definition with respect to the bus, which involves communication with the arbiter and grant signals, as well as the response signals coming from the slaves, makes the transaction much more complex than that of accessing a simple memory. Okay. So, the bus structure, since it needs to deal with a variety of devices, so the signal definitions, the protocol definitions is much more complex than that of a simple memory interfacing. In fact, memory also is of different speed, okay, and that is precisely the reason why we need these kind of a variety of signals. Okay. And to speed up, in fact, to club transactions together, you have the information about this, about the next transactions which will take place. To implement the protections, you have got the protection signals defined as part of the bus itself. Now, the interesting feature is also you should note is this is on chip bus. So, for this bus there are no mechanical parameters really specified. Now, how does ARM core interface with AMBA? Let us take simple example of ARM7, and we have seen ARM7 signals. So, ARM7 signals is not directly or strictly compatible with AMBA signaling standards. In fact, they do not translate directly. So, typically you need an interface unit for decoding and translation to ASB or AHP signals. Okay. Some signals may be just renamed when it is directly there. And so, this is what is important when I am using a IP core. So, if I choose to design an IP core compatible with the bus, I need to define also the interface unit which will make the core compatible with the bus. So, here it is an example of what we say that bus interface, which is nothing but a AMBA wrapper. Okay, it is wrapping the basic CPU. So what we are looking at is, you have got these AMBER bus inputs, these are your AMBER bus outputs, okay, and this is primarily with relation to ASB interface. So these ASB interfaces, so you will find some difference in the signals with respect to the AHB signals that we had discussed earlier. Now here what you have got the signals coming from ARM7, this is basically the ARM7 TDMI AMBER related signals which are directly available, and these are interfaced onto the AMBER bus, okay. So you will find that here in fact the signal, the H ready that we had discussed in case of AHB bus, here it is B weight in, okay, because the definition is slightly different in the ASB bus. So this is B weight in, and which is equivalent to that of N weight on the chip itself, okay. Similarly, you have got the sequence, this tells you, in fact we have used to see how this can be used for accessing DRAM in a bus mode where I can get data from, after selecting a row from consecutive locations. So this would be used in kind of defining what kind of transaction is actually taking place. Also the size information, when we provide in AHB bus, that size information would be obtained from the outputs provided by the ARM chip. So this is basically an interface unit. So with the CPU core, typically you design an interface unit to provide it with the ability to communicate on the AMBER bus. The next thing is your peripheral bus, okay. So the APB or the peripheral bus is designed to support what we call low speed peripherals such as UARTs, keypads and general IO, parallel IO. All bus devices in this case are slave to the master, okay. What is the master in this case? The bridge, okay. All bus devices are slave to the master. If you remember, I said basic definition of a bridge is a slave in the high speed bus and master for the low speed bridge. So here all devices are slaves to the master, the bridge to the AHB or ASB system bus. It provides a simple address with latched address and control signals for easy interfacing. An APB can be implemented with a single tri-stated data bus. So it's very similar to kind of a bus which you encountered with 8085 or 8686 family. And so it has got also the latched address, the address gets latched, and control signal. So it's a very simple straightforward bus. So an APB bridge, now we talk about, instead of AHB was master, now here it's an APB bridge. So it will have got a system bus, this is a slave interface, okay, and these are the signals which goes on to the bus. So it basically selects the device, okay, it has got, it enables, this is basically the strobing signal for operations on the bus. Then these are address and control signals, okay, and this is a write bus, this is for writing the data, and this is for reading the data from the master, that is the high speed bus. So the basic operation is very simple. In fact, it does not support busting because we are not really looking at high speed transfer. In fact, each transactions here also consists of two cycles, an address cycle which is a setup state and a data cycle which is called an enable state. So in fact, the basic the cycle definitions are with respect to the enable signal. The bus uses a single clock called PCLK. In setup, what happens? The bus brings P select and the P write up, putting the address on the P address bus. These are the address lines. So the address is put on the address bus. In the enable state, it brings penable up and places the data on the PW data or PR data bus. So, enable is in fact the data cycle, and this data cycle is actually controlled by your enable signal. In fact, the enable signal will be deasserted on the next clock cycle. So, you can realize it is a very straightforward and simple bus consisting of 2 cycles, okay, and that is the typical feature of most of the peripheral buses. Now, if you look at the complete system architecture, this would look something like this, and this is what you should note carefully, because that tells you how a complete SOC architecture internally would look like. So, you have got the ASP, again we are looking at using ASP, these are all ASP masters, because, and this is your ARM7 core, okay, ARM7 core would communicate with your arbiter. This is another ASP master, okay, because there can be multiple masters on this bus. You have got this bridge, okay. Now, this bridge is actually a slave, okay. There could be other slaves as well, but bridge is actually a slave of the master bus, and your peripherals are connected to the bridge, okay. And the master, these control signals communicate from the master signals manager to the bridge, and the whole idea is this data which comes from here can be to any of these slaves, okay. And this response, if you remember, there was a response signal flowing in. So, the slave sends the response signal. So, that response signal goes to the ARM core or to the other master. This is a transfer response. So, what is the response to the transfer transaction which is currently being executed? And this is your data which flows from the slave back to the master. And this is where the arbiter is. So, once the request comes in, the arbiter resolves and gets a grant to the core. Once it gets a grant, then only the transaction is initiated, okay. So, this is a architecture, basic architecture of an SOC using the 2 buses, that is a hierarchical bus structure, and the whole all data transfers here are in parallel. So, they are both actually parallel buses, and this your system bus, which can be ASP or AHP, is capable of handling a variety of complex transactions, and these gives more flexibility and speed to the bus. In fact, bus as such is a key issue for any kind of SOC designs for embedded system. I may have a very high speed processor, but if I do not have an efficient bus transaction protocol design, then I cannot really exploit the processor features. In fact, I may have multiple processors, but I shall not be able to exploit their characteristics optimally until and unless I have designed an optimal bus connecting them, as well as with the memory and peripherals. The other issue, other trend which has developed related to bus for SOC is what is called open core protocol. In fact, the example that we have seen so far is that of a particular bus, in fact proposed and used and popularized by the ARM processor manufacturers. So, it has got a definite transaction definitions, it has got a specific signal definitions, and when you are designing an SOC, you are picking up the modules compatible with this bus structure. This open core protocol, why we are discussing it here, is conceptually different. What it tries to define is a comprehensive bus independent high performance configurable interface. In the earlier case, all your interfaces were predefined and you are actually making your IP cores compatible with those definitions. Here what we are talking about is a kind of an open core protocol. So it defines a comprehensive framework, and using this framework you can actually design and implement components in an SoC. So it provides a kind of a communication interface. And why it is bus independent? Because you will be actually defining the bus which is consistent with the protocol. Because a protocol can have a variety of transactions defined depending on your requirements and the device characteristics, you may define the bus. But if I pick up an IP core and if I say that my IP core is compatible to that open core protocol, that means it can support the transactions which are being defined as part of this protocol. Okay. So what in this context, it is synthesis timing analysis friendly because I have to put everything together to synthesize the chip, and it encompasses entire core and core or system interface needs, that is data, control and test flows. Test is another important issue. Okay. So basic idea, look at this, that I have got this IP core. Okay. These are different IP cores. This is basically my on-chip bus. Okay. And these on-chip bus have to be definitely in a hardware implementation in terms of a signal. But these requests that my master and the slaves would make, these requests or the transactions are defined through this open core protocol. Okay. So once these transactions are defined through open core protocol, so there is a standardization in the nature of transactions. Okay. So try to understand this. This in case of AMBA bus had what? A set of signal definitions as well as a set of transaction definitions. In fact, we had discussed for AHP bus transactions like burst mode transactions, then transactions with security features, split transactions. So all these transactions are defined as part of that bus definition itself. Here what we are trying to define is basically the protocol for these transactions. So if you have a standardized protocols, basically the IP cores would be compatible with these protocols. So there are protocol phases, in this case in the standard. If you look into it, you will find a very similar kind of a protocol, but just structured in a slightly different way. You have got a request phase which begins the transfer, master presents request, command, address, etc. There is a more elaborate definitions, I am not going into it, I am just giving the basic idea. Response phase is ends transfer, slave presents a response, success or fail or read data. If it is a read operation, it has to be data to be presented to the master. And this response phase is typically available for read transfers. Okay. In fact, if you see that there also similar thing was also there in the ARM, but here we are trying to evolve into a generic protocol phases and protocol definitions. Similarly, there is a data handshake phase which we say as part optional as part of your protocol phases. So what we say is that allows pipelining request ahead of write data, okay, and only available for typically write transfers. So the phase ordering typically for a transaction would be request, a data handshake followed by response. In fact, this is a generic form of most of these protocols, and open core protocol is basically just defining these protocols for transactions on the bus. And how do you use this protocol? A designer selects only those signals and features from palette of OCP, what we call open core protocol configurations, needed to fulfill all of an IP core's unique data, control and test signaling requirements. So try to follow the difference. In case of AMBA, it's a complete specification. In this case, it's not a complete specification. You are defining a standard and you have got the devices or the IP codes which are compatible with these protocols. Depending on what are the features you will be using in an SOC? You can pick up a set of signals and define your actual bus, because using those signals you will be implementing those aspects of the protocol which is required for your SOC. So therefore, your platform becomes more flexible. Okay? Your choice is more flexible and generic. In fact, this is a trend which is emerging for defining buses in an SOC application. Next, we shall look at serial buses. In fact, when we have looked at this SOC and PCB based application, this whole concept of the buses had been parallel data transfers. If we are transferring 32-bit, I shall be transferring that on parallel lines. Obviously, this can be used for short distances that within chip or within card. The serial buses that we are now talking about, this is also for short distances, not really very large, and the basic idea is for moving data quickly from one device to another. Okay? And the basic objective is, obviously, if you have serial protocol, your wiring requirement is minimum. So if you are trying to put a complex system, okay, that is, you are starting with a PIC microcontroller, and with PIC microcontroller, let's say you want to interface additional devices and putting them into an appliance, a box. Now obviously you would like to use minimum number of wires, signaling wires, to do the connectivity. If you are using your PCI or ISA, it has got an elaborate number of signals and its signal definitions, which itself would occupy space, and your cards have to be compatible with those definitions. If I use a kind of a serial protocol, I have only very few signals to connect, so my footprint can be further reduced. And in fact, that is precisely the reason why this kind of I2C, SPI, this kind of serial protocols or serial bus protocols have become popular and being widely used in embedded systems. The whole idea is low complexity as well as low cost, and it is meant for short distances inside the box itself. Okay? So it is not really on chip. In fact, we can have on chip as well, but typical use is within the box. That means maybe connecting a PIC microcontroller with another device. I2C, in fact, the basic name is inter-integrated circuit communication. Okay, this is for communication between two ICs. In fact, it was developed by Philips Semiconductor for TV sets in 1980s. So it's a pretty old kind of a serial protocol. So originally what was it being used for was, it was used as a control interface to signal processing devices that have separate data interfaces. For example, RF tuners, video decoders. In fact, originally it was being used for this kind of tuners and other applications. Today, it's also used for RF tuners, video decoders, encoders, and audio processors. Now, what does this mean? It means that, see, these devices will be transferring, say, let's consider a video decoder, okay, so, or an audio processor. It would transfer the data through a separate data bus, okay, and so they have a separate data interfaces depending on the task. Now, these devices have to be controlled, and this control scheme is not always very simple and straightforward. Okay, you need a set of control information. There may be a set of instructions which may be sent to the audio processor to do a variety of tasks. Okay, now you need a control interface for doing that communication. In fact, I2C is used for that purpose. In fact, I2C devices include EEPROMs, electrically erasable PROMs, thermal sensors, real-time clocks, and many sensors are actually used with this kind of I2C devices. What are the I2C features? Here, the data can flow in both directions. Okay? but it has got two wires, just the clock and the data line. So it's not a full duplex communication, but actually an half duplex communication. It's a synchronous bus. So the data is clocked with a clock signal. In fact, clock signal controls when data is changed and when it should be read. Okay? In fact, that clock maintains the overall control. The clock rate can vary, unlike asynchronous communication. Okay? In an asynchronous communication RS-232C, you have to have a fixed clock rate because you are sampling the bits. That means you are finding out whether there is a start transmission or not at the clock intervals. But since here the clock is being transmitted along with the data, the clock determines the valid data transition. So there may be change in the clock speed as well. In fact, typically you have got 3 speeds: slow, fast, high speed. This is I2C version 2.0. We shall primarily talk about the older version, which is slower, and between these two. So I told you already, my I2C is typically a serial connection. Okay, it has got it is a two-wire bus. One is called your serial data line, another is serial clock line. In fact, your data, so what we say that actual bit transfer takes place when your SCL, that your clock is 1. So SCL equal to 1 implies SDA is having valid data. Okay? So the data needs to remain valid during the high clock. Okay? And the data changes during low clocks. Okay? So the transition would take place during low clock. So the data transition takes place when the clock is low. So change of the data is allowed when the clock is low. Okay? And this clock is actually therefore controlling whatever bus transactions that take place on the I2C bus. The basic protocol is a master slave protocol. In fact, there is no external clock generator. Okay? There is master device, the current master. In fact, master and slave can be again interchangeable. Current master can become slave for other application. So master device controls the clock. The slave devices may hold the clock low to prevent data transfer. Okay? So master is driving the clock. If slave, and there is a single clock line to which the slave is also connected, slave can pull the clock low. If slave pulls the clock low, then your data is no longer valid. So effectively, the master is put into a wait state. Okay? So no data is transferred unless a clock signal is present. So if a slave pulls a clock low, then no transfer can take place. So if there is a speed mismatch, then the slave would do what? Simply pull the clock low. And all slaves are controlled by the master clock. Obviously, this implementation would require a kind of a wired AND connection. In fact, all these interface lines are part of open collector or open drain connections. Okay? So you have to put pull up resistors, okay, to connect these interface lines, okay, connecting them to the actual supply high voltage so that they can become operational. So since it's wired AND, you can understand that the normal state would be high. So when there is no transmission, there will be high, and if there is a one of these slaves pull things down, so it will be low across the bus. Okay. So you can realize that using just two lines, the way by defining the circuit connection, a pretty sophisticated protocol can be done. Obviously, it is not as sophisticated in terms of the protocol as that of your ASP and AHP, but still you have the features of multi-master control, arbitration, everything is built using just 2 lines without involvement of an external arbiter. In fact, this is what we shall discuss in the next class. So, here what we have done, we have studied today the bus specification used typically in an SOC, looked at the basic serial bus for connecting devices to microcontroller, and we shall learn more about the serial buses in the next class, because you have got SPI bus, also there will be the bus definitions for connecting peripheral devices. Okay. So, other bus definitions, in fact, particularly for the IO devices like your USB, FireWire, we shall look at them in the next class. Any questions?
So, in the ARM bus, do we have to change the IP code, like for making it compatible with the bus? Do we need to change the IP code?
The question is that for making the ARM core AMBA bus compatible, do we need to change the IP core? We are not talking about changing the IP core. What I had shown was an interface unit. So, you design an interface logic so that the signals become compatible with the AMBA bus.
But for the other bus, we don't need that, like the open core one.
Yeah, open core, it's a bus. So what we say, it's a bus independent. It's a definition of a set of protocol for bus transactions. And on the basis of the protocols, a designer can select the set of signals to define the actual bus requirements. Any other question? Yeah. So, posted write is if I write, say the basic idea is that I have asked for a read operation. So, and then I have got a write posted. Okay. So, posted write is I have put in a write request, okay, and I have sent the data and I am overlapping it with the corresponding read. Okay. So, I said that that operation is available only during read. So, if we look at it, so slave presence response is a response phase, success fail. So, it's only available for read transfers in the sense that posted write model, that is you have posted the request, okay, and then you will be doing it later on. Okay. So, a kind of a response phase tells you that whether it's a successful or failure, and it can be even done later on.